Hello, CIS40A. In this video, I'm going to talk about Unit 5 lecture, which is from Chapter 5 in our textbook. And in this chapter, we're going to cover TCP/IP model. In the past, we have talked about OSI model, so we're going to take a look at how is it comparable to OSI model. So in the industry, they would refer to a 4-layer model, TCP/IP, and compared to the OSI model, you would see that the first 2-layer network interface would represent data link and physical in the OSI. The network is comparable to the network in the OSI. Transport is comparable to transport in the OSI. And lastly, the last 3-layer in OSI, application presentation and session, is comparable to application in TCP/IP model. And in the image here, you can also see that some of the common protocol will be listed. So at the application level, you're going to see HTTP, FTTP, Telnet, NTP, DHCP, and ping. And ping also work in the lower level as well. So, but on the application layer, if you're using ping command, that will also execute ICMP on the network layer and some of the transport area. But anyway, you would see that there are comparable layers in TCP/IP model to the OSI model. So make sure that we know the structure of TCP/IP model and how it's compared to the OSI model. Some of the protocols that would represent each of the layer, and so on. So that's important. Now, the second image here provides you with the security protocol for the layers compared to the OSI layer. So in the TCP/IP layers, your application layer would consist of PGP, which is pretty good privacy, and also SSH. SSL and TLS actually happens in the TLS sublayer of transport layers. So you would see TCP happening there along with TLS happening in a sublayer. And then IPsec is used in the network layer, in which normally IP would be used, but IP security would be used in a network layer. And then PPTP and L2TP happens in the data link layer, and scrambling and hopping would be in the physical layer. So you would see additional details about security protocol, which your book also mentioned as well. So from the top down, we will take a look at the application layer. This is responsible for making network requests and servicing certain system and receiving after the request was submitted. If the user is submitting a request to a web server through the browser itself is an application, and so the browser is running at the application layer. And so when it's submitting the request, you would see that it would go through some of the lower layer like network, transport, and then when it established communication, you see session and then eventually application. So it would then come back to the top layer after all of the other layers have fulfilled its service for that particular request and reply. So the protocol that you would see in the application layer would be, one of the protocols is your network time protocol. This allows us to synchronize PCs across the network and also with network that would in the external network or the wide area network. And this is what you would see when we have time change. It would automatically sync your mobile phone to your service provider. And also internally, if we're looking at local area network, NTP acts as a way that we can synchronize all our PCs for in case we need to be able to transfer data, replication across the servers. Time is important. And so when you're looking at the primary domain controller, that would replicate across subdomain controller, and it would also use NTP servers to make sure that we can synchronize the PC across our networks. Even in some cases, you do have to connect to the WAN in order to connect to your other networks across the country or the world. Then we also have additional protocols such as Network News Transfer Protocol, and this is used to send and receive news article. I wanted to include this along with some of the protocol that was shown in the image, as we haven't touched on these protocol in the past. In the prior weeks, I have mentioned some of the common protocols. So now News Group has been established for a long time, since the 80s, and so this protocol was used to be able to send and receive news article, which is what you still see through some of the email and web services that we subscribe to. Now let's go to the assignment, and we would start answering some of the first few questions. In the first question, it asks you to identify the TCP/IP layers and describe the functionality. So there are 4 layers in the TCP/IP model. Starting from layer 1, you would have the network interface, which is responsible for physically connecting device and linking signal in the devices, especially with your network interface card and your cable. In the next layer, which is network and internet, it's layer 2 in the TCP/IP model. It is responsible for information delivery after the connection is established. So with this, you also have IP in the case where if we use IP security or IPsec, you would see that happening here as well, but it's also handling addresses, routing, and so on, very similar to what you see with the OSI model. Then the third layer of the TCP/IP model is the transport. This is used for connection-oriented communication to establish a session, and you would see TCP happens here. And also connectionless communication, where a session is not established, where UDP would be used here. So TCP and UDP would commonly be found in the transport layer protocol, and as protocol for the transport layer. For the last layer is the layer 4 in TCP/IP model, which is the application layer. This is responsible for network requests from sending computer or servicing a request from receiving the computer. And some of the protocol that you would commonly see would be HTTP happen at the application layer through the browser. And then you also have additional protocol that was listed in the notes on the first page. Now you can go and expand further to identify 2 to 3 protocols for each of the TCP/IP model layer for number 2. So in the first layer, network interface, Ethernet happens here, and that's using standard 802.3. And then you might also use wireless adapter, which uses Wi-Fi 802.11 in subcategories of the classification. So this is where signal is transmitted, and it could be through cable or through the air. In the second layer, network and internet, here you would find IP for addressing, ICMP, ARP, and ICMP. And the notes also give you the breakdown along with the prior chapters also discuss these protocols. In the transport layer, as we mentioned, TCP and UDP would be used in the third layer of the TCP/IP model. And lastly, the application layer, where we use HTTP, HTTPS, Telnet, SSH, NTP, and so on. So those are some of the few protocols that would be used. Now let's come back to the notes, and we would talk about the transport layer a little bit further. So transport layer is used for connection and connectionless oriented communication. So TCP and UDP uses this layer. TCP would have a TCP header, and within for its packet you would see the flags, and the flags are normally identified as SYN for synchronize, ACK for acknowledgement, PS for push, URG for urgent, FIN for finish, and RST for reset. So the SYN flag, the first flag, is assigned to packets that are used to synchronize for the three-way handshake. So once it's agreed to receive information, and it would send a SYN acknowledgement, a SYN flag, and then the system will acknowledge that it's sent. So that will be an acknowledgement flag after it's receiving the synchronization. Now, push flag is used to force data on an application, so that will push data onto the actual packet. Then you would have URG, which is an urgent flag, which specify that the packet would be urgent, so it would take priority. Fin is a finish flag. This is how you would finalize or end the connection. So as it accomplished or finished the connection, TCP can be ended by using fin flag. And then reset flag is used to end TCP conversation impolitely, where it would hang up without saying goodbye. So there would be an immediate end instead of having an acknowledgement of the end communication. And so reset and fin does accomplish the same thing, but reset doesn't wait for the conversation to be acknowledged that it's ending. So below this is going to contain the TCP header. So every packet is sent with the protocol, and it contains the header. And the information would include in the header such as source port, where it's coming from, that's going to be 16-bit, destination port, where it's going to. And it would use a sequence number to make sure that it would rearrange all your data back in order. And it would have an acknowledgement number to be used. So your header length is going to be 4 bits. The reserved bits are 6 bits. And the flags are used accordingly, like what we talked about. And then the window size and advertisement window is adjacent to that. There will be checksum to make sure that everything is intact. If there is an urgency, there will be an urgent pointer. And then there would be options for the byte size, but the data would be included in the body, not inside the header. But it would then also, if there is some optional data information, that will be included in the header. So here it provides you with the breakdown of all the fields in the header. And so with the reserve, it can be set to 0 for future use in case it needs to reserve the packet. And then so also you would see the window size to determine the amount of information can be sent, so that way it doesn't have an excess or under. So with that, what you would have is the TCP header. Compare that to the TCP header, you would have the UDP header, which is UDP uses, it is a connectionless oriented type of protocol. And UDP header doesn't require a sequence of number for acknowledgement, as the data doesn't need to come back in order for it to present it. It just presents whatever that it receives. So at this, it would just send, and it doesn't really need to present it in an order manner compared to TCP. So there's no three-way handshake with UDP. So the header for the UDP is a lot less. And it is definitely lighter compared to TCP. You would only have 2 bytes for the source port, 2 bytes for the destination port, 2 bytes that contains the length of the actual packet, and then 2 bytes for the checksum. So checksum is still there to make sure that it arrives, but at the same time, there is integrity just verification, but it doesn't really need to have some kind of acknowledgement compared to TCP. So UDP is definitely, the header is a lot smaller compared to UDP. So the source port is going to be 16 bits. And then the destination port is also another 16-bit. The length is going to be 16-bit, where it's 2 bytes. And your checksum is going to be 16-bit. So there would be less field in UDP header. Going back to the questions, we can address the next question. For number 3, it asks you to describe the TCP flags, and you can find that in the notes as well. So here we can say SYN flag is assigned to any packets that's part of SYN phases for three-way handshake. ACK is acknowledgement flag to acknowledge that previous packet has been received. Push is a push flag designed to force data on the application. Fin is to finish, and it specifies that you would like to finalize and end the connection. This is how TCP would end politely. RST is a reset flag. It's used to end TCP conversation impolitely without saying goodbye. Now, for number 4, we want to describe the UDP header fields. And the header field would contain source port, which is 16-bit or 2 bytes. This indicates by sending application the information of the system that's sending. Destination port, 16-bit or 2 bytes. It also indicates using the port that's used by the application or target system. And length is going to be 2 bytes or 16-bit. This field is used to specify the size of the UDP header in bytes. And checksum is 16-bit or 2 bytes. This is used to verify the integrity of the header. So those are the fields for the UDP header. Next, we are going to talk about the IP header field. And IP happens to be in the network layer, which is comparable to the OSI and also the TCP IP model. So this is where we would be able to use addresses for delivery purposes. And in this layer, we know that IP, ICMP, and ARP are used. Those are the protocols that's used in this particular layer. So first, with the Internet Protocol, this provides the packet delivery for the higher model. This allows us to route, and it allows us to be able to utilize how the packet can be sent via the network and prevent looping. So IP protocol on the router is responsible for decrementing, which it contains a time to live, so the packet is never going to go on forever, so it prevents looping, and it would terminate at the end of that time to live. Now, Windows operating system, the default time to live is 128, whereas Linux operating system, the time to live is going to be 64. And so it would then end the communication at when that time is expired. Now, IP header in the packet contains some information to help the packet to go from the sending system to the destination system. And IP header is 32 bits. It would contain version, header length, type of service, total length, identification, fragment offset, protocol, checksum, source address, destination address, and optional data information. So the version would be 4-bit, which identifies the version of IP that's used, either version 4 or version 6. So in your network, if you're using version 6, this is included in this field. Or if your network is purely using version 4, it would also be included in this field. So it would be specific because the addresses are different. Version 4 uses 32-bit decimal values, where version 6 uses 128 bits hexadecimal value. For the header length, it is also 4-bit. This indicates the size of the header. Type of service is 8-bit, which is 1 byte. And this is going to specify how the packet is handled by the system, whether there would be delay or it would send right away. The total length is going to be 16-bit, which indicates the complete size of the entire packet. Identification is 16-bit or 2 bytes. This is where it would specify the maximum size for the transmission, which is maximum transmission unit MTU. And this allows us to break the data into sub-portions or different portions where it would be able to identify fragment of your data. IP flags is 3-bit. This specifies how the fragments are going to be dealt with once it gets to the destination. Is there going to be more fragment or there's no fragment, where it would indicate as MF or DF. So if there's fragment, it would then use MF, and if there's no fragment, the bit would include DF. Then if there's fragment, it's going to also specify the fragment offset, which is 13 bits field. And in this fragment, it would use the offset to put together the order of the fragment when the packet is assembled. Time to live is TTL, and this is 8-bit or 1 byte. This specifies the time that the packet would expire, so we would prevent looping. It would then be discarded when TTL reaches 0. So in the Windows system, if it's 128, it would then count down until when it reaches 0. If it's not able to reach the destination, then it would just be discarded. Protocol is going to be 8-bit. This is the field where it would contain the information about the protocol, whether it's TCP or UDP. And so when you use the packet monitoring this week for Microsoft, you would see this particular section where it would include the protocol information. Then you have the header checksum, which verifies the integrity of the IP header. Then you also have 2 additional fields which contain 2 bytes or 32-bit. This represents the IP address of the sending system for the source, and for the destination address, it represents the IP for the receiving system. Then the options is a variable field in case that it needs to include any other settings that pertain to the IP header. So in your questions, it asks you to specify in IP header what field specifies when the packet is to expire, and that will be your time to live, or TTL. So when that becomes 0, that packet would then be discarded. For our next section, we're going to talk about ICMP. And ICMP is Internet Control Message Protocol. This is a way that the network can share status and error information. This is used to troubleshoot or detect network systems. ICMP are encapsulated within IP datagrams, so it can be routed throughout the network, within the network, and outside of the network. There are 2 programs that uses ICMP, which is your ping and your trace search. So ICMP is always going to tie to ping, and ICMP is going to tie to the application trace route. Trace route is used to follow a packet, so it's actually pinging the systems that's receiving it, the destination from the source. So when we use ping, we would send an echo where it's going to ask for the response. So when we would do ICMP, when we ping, it would do ICMP echo request, and it's going to wait for the target system or the destination to respond with ICMP echo response or reply. And with ping, you can determine what part of the network that system would be functioning in. Trace route would allow you to take the path where the host would transmit the connection from one end to another. We will follow the router or the hops. So trace route sends the same thing as ping, so it uses ping in the back, ICMP echo request to the destination system, and the destination system will respond. In the case where it doesn't receive information, it would submit the error, and that error would specify that it's timeout or ICMP time has exceeded. So in the case where you don't receive the reply, very similar to ping, it would say timeout when you do a trace route. ICMP does not use port number, but it uses code to identify the type of messages that it's sending. Some of the ICMP types are broken down into the different type of codes. So type 3 can be destination unreachable. That would then be used part of the error message submitted to the sending system. So here there would be a list of different type of ICMP code. 0 for echo reply for ping, 3 for destination network unreachable, 3, 1. There will be destination host unreachable also. That will be sub part 2 to the 3. And so with the 3 is where you would see that host is unknown or unreachable. And then 8 is for echo request, 10 is for router discovery, and 11 is for time to live is expired. So in the ICMP header, it would look something like this, where your type is going to be 8 bits, code is going to be 8 bits, ICMP checksum is 16 bits or 2 bytes. Your identifier is 16-bit, sequence number is 16-bit. You would have a magic number, IP, port, state, acknowledgement number, length, sequence number, and reserve, and some optional data field. So here it gives you some breakdown of some of the area or the field in the ICMP header. So the protocol that you're using, you would always have some form of header, and that header would contain information about the source to destination, the integrity check, and some time code or things to make sure that it validates the connection. So in the next question, it asks you what is used by ICMP to identify different types of message. It would use codes and types, as we would see how echo request would be a certain code, and when host is unreachable, it would be 3, and then there's subtype code. In the next portion, it talks about Internet Group Management Protocol. This is different than ICMP. This is Internet Group Management Protocol, which is IGMP. This happens in the network layer of the OSI model. It also happened in the same layer for TCP/IP, but it uses multicast protocol. This is used to send to multiple systems at once, and hence the name Group Management Protocol. Is able to communicate with multiple systems at the same time. Next is going to be your ARP, which is Address Resolution Protocol. This provides address to the physical address from TCP/IP network. It would resolve IP to MAC address. All systems in the local area network would own an IP address, and it would tie to the physical permanent address, which is MAC address, Media Access Control Address. And ARP would then be cache, including IP to physical mapping. So it creates what we would logically present as a table where it associates the IP address to the MAC address of that system. The IP address is used for routing, and the MAC address is used for switching. So those type of addresses would be useful in how we would get data from one system to another, route to it, and then switch then to the actual physical system as part of that segment. So in the network layer, you would also see not just IP version 4, but IP version 6. And so running out of address from version 4 was the main motivation in creating IP version 6. The benefits of version 6 include that it minimized the overhead because it's a simple IP header compared to the older version. So it doesn't utilize too much of the resources to process the packet. it does have a larger address space in that it is a 128-bit address versus 32-bit from version 4. It also can use multicast as the core of communication, so it doesn't have broadcast communication compared to IPv4, in which broadcast would utilize a lot of the bandwidth to send out to all the system where it might not even be needed. IPsec for IP version 4, it did not include the industry standard IPsec that would fully be supported, but IP version 6 has the IPsec built into the protocol suite. And that allows us to have encrypted communication on the network, especially when we're working with VPNs, virtual private network. So here it gives you the information about IP version 6. We mentioned that IP version 6 uses a 128-bit address scheme. So that gives you a unique amount of 2 to the 128, where it would be a lot more addresses than what we've dealt with in IP version 4, which was only 2 to the 32nd, which is approximately 4 billion unique addresses. And what it does, it uses 8 hexadecimal block, which is 16 bits each, and it would be separated by the colon. So the example of this is here. This would be an example of an IPv6, where you would have the digits, and the digits are separated by the colon. And IP addresses for version 6 is not case sensitive, but you can have a shortened or a compressed address using a double colon. Just means that there are zeros in writing out the addresses. So an example of a loopback address is all 0 with the ending 1. So what we can do is we can shorten it to remove the leading 0, and it would look something like this. Or you can convert them all to 0 by using a double colon, and a pair of double colon is also used only once. And you can do this for IPv6 that has multiple contiguous block of zeros. So if it's 0 in the between like this, we can shorten it by indicating a double colon like this, or we would have a single colon just to remove the leading 0. And there are multiple ways to write your shortened address, especially when you have to shorten the 0. There are three types of your IPv6 addresses. There's unicast, where it's used to send one-to-one for the communication. Multicast is used to send one to many systems, a group of systems, and it would start with the prefix FF01. So when you see this, you would know that this is the multicast. And then Anycast refers to a group of systems that providing a service, but that there is no broadcast here. So Anycast is not quite broadcast, but it's just a group of systems that's used for service. So in the next question, it asks you to identify the type of IPv6 addresses, and that will be unicast, multicast, and anycast. So make sure we know the difference for Network Plus, certification, and your quiz and exam. There are 3 types of unicast address. There's global, site local, and link local. And let's take a look at the difference. The global unicast is for public address that's external to our local area network. Site local is used for private address that would be inside the network. And link local is used for link only. So when you come back to the notes here, it talks about type of unicast address on page 8. Global unicast is a public IPv6. This is used to route across the internet. This is a global unicast address that's equivalent to public IPv4 address. Site local unicast address is a private address that's used within the network. This is used for local area network communication, and the unicast address always starts with FEC0. So when you see this, that will be just a site local unicast. Your link local unicast, that will be unicast address like automatic private internet protocol, your IPv6, and this can be used to communicate other nodes on the link, and link address starts with FE80. So when you use FE80, as you've seen with the RCCD network that we looked at, right? They use this, that's just because they're using link local unicast, which is an IPv6 address. It's not really fully activating or implementing IPv6 address. But internally, if you're using this at home, FEC0, that's just for internal address, and it's a private address. It's used to go one-to-one. So here we specify the 3 types of unicast address. Make sure that we understand the difference. Now let's talk about hexadecimal conversion. When you have decimal number, which is our counting number, 0 through 9, your hexadecimal is 0 through 9. And this will be your binary. When you have a number 10 in decimal, which is your counting number, your hexadecimal will be equivalent to an A. And in the last week, we already talked about the binary, so I give you some of the binary details here. Number 11 is equivalent to hex B, 12 is hex C, 13 is hex D, 14 is hex E, and 15 is F. Now, each of the character for IPv6 address or hexadecimal is made of 4 bits. This means that each block would be separated by a colon is 16 bits in length. So there are 8 blocks, which is going to be 8 times 16, which gives us 128 bits. So we can calculate the 4 bits by taking the decimal number, for example, number 7, which is going to give us 4, 2, 1, and that will be 7 in decimal. So when we look at another value in the following example, so if we have FE80 here, this is going to represent the F is going to be 15. So we would have 15. F in 15 is in decimal, and that would be equal to 8 plus 4 plus 2 plus 1, which gives us 15. So that means that the binary for all the bits positions are on for those 4 bits. So now what we can do is we can convert this into binary. You can definitely put this into a programmer calculator, but it's really easy. So if I start with the first one, the 2 is going to be equal to, and you're going to go from the right side first. So if we have 1, 2, 4, 8. Let me point back to this. So the first bit on the right is going to be equal to 1 in decimal. The next one is going to be 2, and then the following is going to be 4. So let me copy this over, and so I can show you. So in here, we wanted to include this on here so you can see. So we want to find the binary for the number 2. As a hexadecimal is represented in 4 bits, So that means that the first bit is off, the second bit is on, and the rest are off, because we only need to make sure that this is going to be a 2. So a 2 in hexadecimal is the same as a 2 in decimal. So the binary would be this. It's off at 1, it's off at 4 and 8, but it's on at 2 because 2 needs to be equal to 2. So you would have 0, 0, 1, 0. So what you would do is you would start with the decimal equivalent, just like what we did last week. You would take this number and you would go down the line and you can see which number you can subtract with. And the only number I can subtract with starting from left to right is going to be 2. So I put a 1 there. And 2 subtract 2 is going to give me a 0. So I would have a 0 at the 1 because there's nothing else to subtract. So then on the next number, we would have a 6. And so with the 6, then you would start from left to right. So 6 is less than 8, so I can't subtract it. I would put a 0 because a 6 in decimal is equivalent to a 6 in hexadecimal. So I can simply do a conversion with the decimal equivalent. So I can't subtract an 8, it's too large. So 6 minus 4, if I subtract it, I put a 1. And that gives me 2 left. 2 subtract 2, which gives me a 0. So I have nothing else to subtract. So that will be my next 4 bits is 0, 1, 1, 0. And then for the 0, that's easy. All your bits are going to be 0, 0, 0, 0. And for the 3, and so all we know is the last 2 bits, the 1 and a 2 added together is going to be a 3. So a 3 in hex is going to give us 0, 0, 1, 1. So what you can do is you can use the table, or you can quickly determine what adds up to be that number. And so I know that a 1 and a 2 is going to add up to a 3. So as you go, and I won't solve everything. So when you write this out, you would have your answer would start with 0, 0, 1, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 1. And then on the next 4, and that simply is 1, 0, 0, 0, and then the rest are all 0 for this. And then this is going to represent the first. And then so now when we get to the F, we know that F is equal to 15. So we have F is equal to 15. And so you look at this table and you would say, which number would we add up to be 15? All of them. 8 plus 4 plus 2 plus 1 is equal to 15. So that will be equal to 1, 1, 1, 1. And your A is going to be 10 in decimal, which is going to be 8 and 2 to add up to be 10. So I can take 10, subtract 8, which gives me 2 left. I cannot subtract 4, but I can subtract 2, and so on. So when you look at the 4, and the hex is only going to reach 1, 2, 4, 8 scale in the decimal. So that is going to give us 1010 there. And then for our 4 on the next one, that's easy. That's going to be 0100 because the only one that's going to be on is that. So now when we would then find the last one, which is the 0, that would be easy. 0 is equal to 0. So on the next one, we would have 1111, 1010, 0100, 0000. So, and all of that, I just put that over here together so you can see. And then you would continue with the next A. We already found what A is, right? So that's really easy. So we would then have the same as this twice here, and then the 0. So we would have 1010, 1010, and then 000, 0. So that will be the next part here. And as you practice, it's going to get easier as you're familiar with the scale. And you can continue with the rest. So I want you to be able to practice. And so I would just put here, that would be dot, dot, dot. So make sure that you find the rest of this. Okay. So this is how we would convert, and you can always use your calculator. And in order to put in, change this to programmer. If you want the hex value, for example, you would put in a 2, and it's going to give you the binary there. Okay. If I put in the hex is E, it's going to give me the binary there. Okay, so you can use the calculator definitely, but I want you to know how to do the hex conversion. One hex value is equal to 4 bits, so you would always represent it as 4 bit for each of the hex value. Okay, so those are some of the example that you can, and make sure that you complete this. I did the first half. You just gotta convert the last half. Now, what if we go and convert it back? Okay, so I'm gonna go ahead and do 1, which is the A for you. So what I'm gonna do is I'm gonna copy this table with the bit position, decimal, and the binary. And I wanted to, this one, I'll put this as A is equal to 10, which is, okay. Now let's clear out our binary, and we would go through and we would check each one. So if you start with the first one here, if you put all of them in, and that means that we're going to add up all the decimal equivalent. So if all the bits are on, then we're going to add them all up, all of these. So 8 plus 4 plus 2 plus 1, right? So 1111 is equal to 8 plus 4 plus 2 plus 1, which gives us 15. And 15 in decimal is going to be an F in hexadecimal. So this would be Then for the next one, we can use the scale again. We would put in 1101, and we're only going to add up the value that has the 1. So in this case, we're going to add up 8, 4, and 1 because those have the 1s on the bottom. So we would have 1101 is equal to 8 plus 4 plus 1, which gives us 13, and 13 in decimal would be equal to D. And if you're not sure, you can look at your notes. I included a table right above this, and D is 13. And it also has the binary equivalent. So D is the next one. Then we are going to do the next 4 here. So we can clear out our table. We would have 1, 0, 0, and 1. So at this point, what we're going to do is we're only going to add up the 8 and the 1 because those are the bits that are on. So we would add up this right here. And we would add up this one right here because you would see that here's the 1 and here's the 1. So we would have 1001 is equal to 8 plus 1, which is 9. And 9 in decimal is equivalent to 9 in hexadecimal. So this is equal to 9. Then for the next one, we would then take the last one here, which is 1011, and we can then clear out. We put in this in 10 in our table, and that means that we're going to add up that one, this one, and this one because these are the bits that are on. So that's going to give me 8 plus 2 plus 1, which gives me 11 in decimal. And that is equal to B in hexadecimal. So here what you see is for the question A, for number 10, that's going to be equal to FD9B. That's going to be equal to the binary that was. So this is equal to that. Okay. So there you have it. This is how you would convert from binary to hexadecimal. We can use the addition method. We would place the ones here, just like how we did with decimal. So first you convert it to decimal, then you use the scale for the decimal to convert it to hexadecimal. Anything from 10 and above is going to get converted to A, B, C, D, E, F, and 0 through 9 is going to be equivalent to 0 through 9 in hexadecimal. So convert it to decimal from binary and then scale it to the hexadecimal by comparison using the table. And with that, I show you A, you need to do B and C. Next, we're going to talk about octal values. So octal values is the scale for octal is less than hexadecimal. And octal is a number system that's going to only go from 0 to 7, which means that it only has 3 bits. We have the first, the second, and the third. And in decimal equivalents, you have 1, 2, and 4. So it's 1 bit less than hexadecimal. So when you convert this, you would see that here. So if I have a 7, that will be same way that I did the conversion with hexadecimal earlier. I would do the subtraction going down the decimal scale. So 7 minus 4 minus 2 and minus 1. So as I subtracted, I would put the 1 there, and that's going to give me the binary equivalence. For the 3 in octal, that's going to give me a 2 and a 1. So we would have a 1 and a 1. So in the front of that will be a 0. So let's try with the octal. And I'm going to do A so you can see. So what we can do is we can take this scale, we'll just copy this, and we would use the scale so you can see. And we would clear this out. Okay. So I need to convert a 2 of octal into binary. I look at the decimal equivalent just like before. Which number can I subtract? I cannot subtract 4 because it's larger. So that will be 0. The next number I can subtract 2 with is a 2. So I put a 1. And 2 subtract 2 is going to give me a 0. And 0 cannot subtract a 1. So I put a 0. So for my first number, a 2 is of octal is equivalent to 0, 1, 1. Then the next number is the 4. So again, I can clear this out and use the same scale. So I need to go a 4, so a 4 can subtract a 4, so put 1 there. And 4 subtract 4 is 0, so there's nothing left. I would have a 0 here and a 0 here. So that means that a 4 octal is going to be, and that's a base 8, 1, 0, 0. So when you have this number, it's going to be equal to 0, 1, 1 and 1, 0, 0 in binary. Okay. So with that, very similar process to the last hexadecimal, but just octal has 3 bits, so it's 1 bit less, and you can use the subtraction method there. So you can do B and C for this question. For number 12, we need to convert the binary values into octal. So I'm going to go ahead and do A. So again, we can take the scale that we have for the decimal, and we're going to go ahead and clear out our binary here to start. So we're going to start with the 100. So we would do 1, 0, 0. So since the only one that's on is the 4, then we can say that that's a 4. The rest is off there. Then let's clear out. our binary again, so that will be 101. So we're going to go ahead and add that one. And we're going to add that one because this one is on and this one is on, the middle one is off. So that's going to give us a 4 plus a 1, which is a 5. Then, so this is going to be a 5. Last one is going to be 0, 0, 1, so that's easy. We clear this out. So we put in 0, 0, and a 1. And the only one we're going to add up is that one because that's the bit that's on here. So that is a 1. So we would have a 1 there. So that means that this octal value is equal to this. So there you have it. 451 in octal is equal to 100, 101, 001. So, and as you see, it's different than hexadecimal that it is only 3 bits, not 4 bits. That's what makes it octal. And the maximum value that you would have is 7, as you would have 1, 2, 4 for the scale. So with that, you need to do number 12B and C on your own. Then in the next part, what I have is I have you look at this IP, and you notice that we would have this number here is 0 and this one is 0. So we can do truncation with or shorten by using the 0 there. Now when we shorten these two, we would indicate it as this. And when we shorten this part, we would use this. Okay. Or another way that you can write this is that we would do the front is going to be shortened, and then the back is going to be the double colon. So either way would be fine. And you can visit the website. So if we click here, it's going to take you to the number representation. So here it talks about how it's 128 bits with 8 groups. So each group is 4 hex digits that represent 16 bits. Now when you shorten it, you can use a double colon like this, or you can use the 0 leading. So you would have a 0 leading 0. Now if you want to, and you would see that sometime you would omit the 0. So you can take out the 0 in front of this one, the 0 in front of those two, the 0 here, 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 and here. So we can remove the leading 0 there. And so that would be represented like this. Now in the combining the rule, it says the shortest possible representation is achieved by combining both rules. So we would then shorten this. You can never have a 2 double colon or 2 section of double colon at once. So you wanted to have this part here and this part here as a double colon, and then you would remove the 0 in the front. You would have the digits only because they are significant compared to the 0. So the common mistake would be that you don't shorten them appropriately. We never use the double colon like this twice. So you would only use it once, and then you would use the leading 0 to represent the other section if there is 0. And also, you don't remove the trailing 0, you only remove the leading 0. So this one is also incorrect. So make sure that we know how to use the IPv6 in the format here. So when you do this, so we remove this, you see, that is removed. We also remove this one. We are removing this one. So we're left with only the significant character, not the 0. And then we would use the 8 bits here to indicate with the double colon. And then the 8 bits that has 0 here, we would just follow it up with the 0 and a 0. Then you can also read the information about the prefix. So when you look up the information from that website, it talks about the prefix length. And this is often referred to as a CIDR or the CIDR number or value. It is a decimal value that shows the number of leftmost bit that the address network portion is used. So if I put 64, that will be all of these to the left. 64-bit that's used. If I use larger, or if I use 32, only the first 2 section that's going to be used, or 32 bits. So this allows us to really indicate the length of the subnet mask in IPv6. So it's like equivalent to for the 255 that all of them are on, but because IPv6 address is going to be longer. So here you can see that if you have a /4, we would have 128 or 124, 2 to the power of 124 total addresses left as we're using the 4 bits. Why is that? Because you would take 128, subtract 124, which gives you the 4 bits. If we use 8 bits, we would be left with 2 to 120 power for the total addresses, as we already use up the front portion for the network. So as you can see how the network portion for the example address would be scaling out. If I choose 32, I just take 128, subtract 32, I would be left with 96, which gives me 2 to the power of 96. So for number 14, if I use 4-bit, that means that I have 128 bits in IPv6 address, subtract 4 bits, which gives me 120 bits for host. So that means that it's going to be 2 to the power of 124. Now the same thing here, if I have /24, I would then take 128 bits minus 24, which gives me 104, and you would use that as the exponent for 2 to the n. And 2 to the n is equal to 2 to the 104. So you simply take 128 subtracted by the CIDR number, which gives you the exponent number for your host address. And the same thing that we do here for C, we would take 128, subtract 64, which gives us 64, and that will be the exponent of our host, 2 to the 64. Pretty straightforward. So IPv6 breakdown. And to go back, and we talked about CIDR earlier, and we calculate the value. So CIDR is known as classless interdomain routing. This was used in IP version 4. It's a way that we would be able to identify the network ID. So if we use the 48 bits in the IP version 6 address, that will be assigned to your organization internet service provider. It's given to you by the site. So that will be the first 48. Your subnet ID is made of 16-bit. This is going to divide it to multiple subnets. So if you want to create 2 subnets, then you would look at using the network ID that we previously used, and then we would then specify the 2 here. Then your unique identifier, which is going to be the last part of your IPv6, and that is going to be your MAC address. So the last part is just going to be made up of your system MAC address. So the first is the network ID that's given to you by your ISP or the organization internet service provider address. This is a global address. Then your subnet is going to be the value for the 16 bits that's going to be identified to what your subnet mask equivalent would be. So if I have 1, I wanted to make 2, I would do a 1 and a 2 there for 2 of my network ID. And then the last part of your IPv6 is going to be your MAC address, which specify the values that will be placed there. So your EUI. And you can look at your IPv6 address representation. Now in auto configuration, IPv6 is generated using their own address to then allow you to have unique address in the network. In the case where if a neighbor system is want to use that, it should then not duplicate the address because the MAC address is different, and it's able to auto configure the addresses. So there are protocols that uses IPv6. IPv6 is one of them. ICMP is another one. DHCP is another one. You also have MLD and ND, which is neighbor discovery. that's used on the router, which uses ICMP or ping. And you also would incorporate ARP with neighbor discovery. Multicast listener, your MLD, also function with ICMP. So some of these listener discovery type of service uses ICMP v6, and then router advertisement uses IPv6. So at home, when you're looking at your wireless router using your network monitoring tool, you would see IPv6 or version 6 of ICMP. So in the next few questions, it's going to ask you to answer this. For 15, how does the computer system generate its own IPv6 address without using the same IPv6 address of another network? It uses the auto configuration process. It would generate an IPv6 address, then check to see if it's already in use in the network through neighbor solicitation message. So it's just to check to see if any other people would have that address. If another system already used the address, then that system would then respond to the solicitation from that host, and it would notify the host that that address is already used, so it won't be duplicated. The protocol that replaced ICMP from IPv4 is your multicast listener discovery, and that's your MLD, which uses ICMP version 6. For 17, you can go to Tunnel Protocol section on page 11. This talks about different tunnel protocol, and this is used for us to establish secure communication. IPv6 uses the dual stack protocol, which run alongside with IPv4, and that allows you to carry IPv6 traffic across an IPv4 network where you can use it on top of IPv4. So the tunnel protocol would be 624, which automatically tunnel the protocol, and it uses ID 41 to indicate that it is encapsulating on IPv6. Teredo is an automatic tunnel protocol, and this allows you to use network address translation device, such as a NAT server. ISA TAP is going to be 624 and Teredo combined, and it allows you to do intra-site automatic tunneling address protocol. Merito is going to be for Linux use, and that is a Teredo tunnel client. So Teredo is for Windows-based or non-Linux, and then your Linux use is implementing 624 by using Merito. So 4 to 6 is a way that we can encapsulate. You can use IPv4 over IPv6 network, so it's reverse of 624. Now, your network services, we know that when we look at your network monitoring, you would see a lot of different network services. So for your web services, you might use IIS for Windows, Apache for Linux, and that's to handle HTTP requests for your web server. Your network controllers with the DNS, DHCP, and also convert fully qualified domain name to IP, which is your DNS. Now, network controllers also pertain to the Active Directory, how it sends and receives data on the network. Your RDP for remote desktop, WINS for converting NetBIOS name to IP, NAT, PAT, and SNAT is to translate private to public IP. So make sure for Network Plus we know some of these protocols and what they do, how it relates to each service. SMB is used to share files and printers. ICS is used for shared internet connection, like how you would be doing tethering. And NFS is allowing you to access files that store on a remote system. Samba is used to share files and printers in Unix or Linux system, and so on. So some of these are listed. They might be newer to you, as you already know some of the simple protocol that we've been covering in the past. But make sure that you know most of these protocol as they are used in the network, and it might come up on your certification. So in the last part, it asks you to first identify the IPv6 tunnel protocol that's used by the router to determine the endpoints. That will be 624, Rito, and Torito. For number 18, it asks you to identify the network services given by the scenarios. A, to share file printer between Windows and Linux client system. That will be Samba. B, to resolve convert NetBIOS names to IP address. That will be WINS. C, translate private of public IP addresses. That will be your NAT, network address translation. D, plan, document, and manage all the IP subnets. That will be IPAM, or you can say IPAM. And E, remotely connect to Windows network to access files and application. That's your remote desktop protocol, your RDP. And F, to minimize the configuration client by broadcasting services in the network to clients. That will be zero config. And all of this information can be found on the last page of your note. And this concludes my video for Unit 5 lecture in CIS40A. Thank you for watching the video. See you next time.